Everybody, welcome to today's lesson. Today we're going to be talking a little bit about what is called the combined gas law. And what's really, really cool and interesting about the combined gas law is it's going to take all of our knowledge from Boyle's law, Charles' law, and Gay-Lussac's law, and literally, as our title would suggest, combine them into one gas law. So why would we need to use the combined gas law? Well, more often than not, we actually don't have any conditions that are held constant. So in Charles' law, we have pressure that's held constant. In Boyle's law, we have temperature that's held constant. And in Gay-Lussac's law, we have the volume that's held constant. But in the combined gas law, we actually don't have any variable that's held constant, and all variables are changing. And so I really want you to just kind of take a minute and pause here, taking all of this information, taking all three laws, PV equals PV, V over T equals V over T, and P over T equals P over T, and I want you to see if you can think or predict of what that combined gas law may look like. So go ahead and take a moment and pause now and make that prediction. Okay, welcome back. So if we take again our three laws, and I'm going to write those all out at the top of the sheet here. Okay, so we have PV equals PV. Okay, we have V over T equals V over T, and we have P over T equals P over T. And I want you to take a look at how in each of these equations, we can connect that equation to the next. So notice that V is in the numerator for all of these equations. Okay, notice how P is in the numerator for all of these equations. And notice how T is consistently in the denominator across all of these equations. And so when we take this combined gas law and we push it into one, we end up with P1V1 over T1 equals P2V2 over T2. And this is our combined gas law. And what's really nice about this gas law, and I'll show you this at the bottom of the sheet, but we can essentially derive any equation that we want from this one combined gas law. I also would like to take a moment and just point out that this is actually the only one of our equations that's found on the reference table, but this is on reference table T, and it's available for you so that you do not need to memorize this equation. Okay, so let's go ahead and take a moment and practice solving something that involves the combined gas law. Now, again, like Gay-Lussac's law and like Charles's law, we do want to make sure that anytime we see temperature, that we automatically put into our minds that we need to use Kelvin as our temperature. So we are going to have to convert this by adding 273 in order to solve for Kelvin, okay, giving us 298 K as our initial temperature. Now that we have this information, let's go ahead and plug all of that into our equation. So P1V1 over T1 equals P2V2 over T2. Okay, so we have an initial pressure of 3 atmospheres. Okay, an initial volume of 1.5 liters, and an initial temperature of 298 Kelvin. And we are looking to solve for our final temperature. So let's plug in all of our final conditions. We have a condition of 1.5 atmospheres. Okay, we have a condition of 6 liters, and we have X Kelvin as our answer. Now, I'm a big fan of personally solving out the entire left-hand side since we have no variable there, and then solving from there. So let's go ahead and do that. So we have 3 atmospheres multiplied by 1.5 liters divided by 298 Kelvin, and that's going to give us 0.0151 is equal to 1.5 times 6, giving us 9 over X Kelvin. Okay, we're going to multiply both sides by X Kelvin. Okay, so X. And now we're going to have to divide both sides by the 0.0151. Okay, so 9 divided by 0.0151 gives us a new temperature or a final temperature of 596 Kelvin. Okay, and that's the combined gas law. What I'd like you guys to do is I'd like you guys to take a moment and pause, and I want you to practice pulling all of the variables out of the word problem on your own. So go ahead, take a moment, pause the video, pull the variables out, and then check back and see if you got those correct. All right, so welcome back. Hopefully you paused that video. If you didn't, I'm sorry, but let's go ahead and go through this together. So suppose we have a helium balloon that is approximately 2 liters at 27 degrees Celsius and 0.50 atmospheres. How would the volume of the balloon change if we're at STP? So we know that we are starting with a volume of 2 liters, a temperature of 27 degrees. Do yourself the favor, automatically change that to Kelvin. So we have 27 plus 273. This is going to give us a nice 300 Kelvin even. Okay, and we are starting at half of an atmosphere, 0.50 ATM. The rest of our word problem says, how would the volume of the balloon change if we were now at STP? So the Regents particularly loves using this concept, this STP, to bury your variables in the word problem to make it a little bit more challenging for you. I do want to remind you that you can locate standard temperature and standard pressure on reference table A. So if you do ever forget that, please do use your reference tables to your advantage. So standard pressure, the first thing that we need to look for. Okay, standard pressure. Now, notice how your pressure is in atmospheres, so you do need to use the standard pressure in atmospheres, which is 1 ATM. Okay, we are looking for the volume. It's our unknown, we're not sure. And standard temperature, again, according to reference table A, is 0 degrees Celsius, and we do need to convert that to Kelvin. This is going to give us 273 Kelvin. So now we can go ahead and plug all of our information in to our problem. So we have 0.50, okay, times 2 divided by 300 equals 1x divided by 273. And so let's go ahead and solve this out. So 0.5 times 2 is going to give us 1, divided by 300 gives us 0.003 repeating. So I'm just going to throw a couple 3's on there. Okay, and this is equal to x over 273. So we're just going to have to multiply both sides by 273 in order to isolate our variable. So 0.00333 multiplied by 273 gives us 0.91. And again, this is liters. Okay, awesome. So now what I wanted to show you, and what I think is particularly amazing about the combined gas law, is that we can derive any of our equations, Gay-Lussac's law, Boyle's law, or Charles' law, from this combined gas law equation. So what I want to go ahead and do here is write out the combined gas law in each of these boxes and show you when we get to a problem how we can use that combined gas law. So P1V1 over T1 equals P2V2 over T2. And I'm going to repeat that across the board. Okay. P2V2 over T2 and P1V1 over T1 equals P2V2 over T2. Okay, so let's say we get to a problem where we end up requiring constant pressure, or our problem indicates that we have constant pressure. Now, if you think about the constant pressure in which problem requires constant pressure, this is Charles' law. okay? And if you look and we just take our combined gas law and plug it in and we eliminate whatever's held constant, notice that we now get V1 over T1 equals V2 over T2, okay? Similarly, if we have something that's held at constant temperature, this is going to be Boyle's law. And so if we eliminate our temperature variable, we end up with Boyle's law, P1 V1 equals P2 V2. Okay, looking at constant volume, again, this is Gay-Lussac's law. Okay, if we eliminate our volume, we now get P1 over T1 equals P2 over T2. And if we have nothing that's held constant, we just leave it as it is. And so even though the Regents only provides you with just the one equation on the back of the reference table, it is an excellent equation because we can find any of our equations from there. Now, one other thing that I know I've mentioned, but I'd like to point out one more time, because you do also need to remember those graphical relationships, the graphs, and whether or not it's the indirect versus direct relationship. And the easiest way that I like to remember that is anytime it's a division problem, it's going to be a direct relationship. So we have our direct relationship as Charles' law and our direct relationship for Gay-Lussac's law, and then Boyle's law is our indirect law. I'm going to hold on to this last problem for class tomorrow just because I don't want to keep this video extra long. So thank you guys so much for watching, and I will see you guys tomorrow.